Section 4.4, Part 4 of direct proof, divisibility. So what does it mean to divide? Again, basically think of that as groups. So here we have an example. We've got 12 objects, and we are dividing them into 4 groups, each of which have 3. So there's a number of ways we can describe this. We can say n is divisible by d, and our definition, if and only if n equals d times some integer, and of course d is not 0. We could also say n is a multiple of d is a factor of n, d is a divisor of n, or d divides n. That last one we're going to write as d looks like a straight line and then n, which again we read as d divides n. And again, we define that as there is an integer, say k, such that n equals d times k, and d is not equal to 0. Let's check some divisibility examples. Is 21 divisible by 3? Yes, it is. Does 5 divide 40? Yes, it does. Does 7 divide 42? Yes, it does. Is 32 a multiple of negative 16? Yes, it is. Is 6 a factor of 54? Yes, it is. Is 7 a factor of negative 7? Yes, it is. So all of those did work. If k is any non-zero integer, does k divide 0? My answer would be yes. I could write 0 as k times 0. Now 0 does not divide k, but k does divide 0. Again, do make sure you're a little bit careful on the order in which you are reading these problems. All right, so we're going to start with 2 theorems. I do not have the proofs at this point. We are not going to hit those in this class. So here we're just going to give them. For all integers a and b, if a and b are positive and a divides b, then a is less than or equal to b. And the only divisors of 1 are 1 and negative 1. So again, we are just going to give you those. All right, let's hit another example. If a and b are integers, is 3a plus 3b divisible by 3? Yes, it is. I could write that as 3 times a plus b, and since that's an integer, I have 3 times an integer. That's pretty much my divisibility definition. If an m and k are integers, is 10 km divisible by 5? So I'm going to write that 10 km as 5 times 2 km. Since 2 km is an integer, I have 5 times an integer, and that, once again, is my definition of divisibility. All right. So again, as a reminder, if something does not divide, then that means n over d is not an integer. So if, for example, does 4 divide 15? No, it definitely does not. If we put that in our calculator, we get a decimal. So it's not an integer. We talked about a definition of a prime number earlier on. We could also say that an integer n greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. All right, so we've got some properties, we've got some examples. Let's do some proving. So my first proof, I've got integers a, b, and c. If a divides b and b divides c, then a divides c. So let's start this out. Again, we want to make sure we know where we're starting. We want to make sure we know where we're going to end up. So let's start with our given. Since a divides b, I can write b equals ar. And since b divides c, I can write c equals bs. Or again, r and s are integers. So let's do some substitution. Instead of writing c equals bs, let's write it as ar times s. Remember, we can multiply in whatever order we like. So I'm going to write that as r, or a times rs. And we are just about finished at this point. R times s is an integer, since everything else is an integer. So we have a times an integer, and that is pretty much everything we need to have. So there is that property then written out. And we talked briefly about this. This kind of follows from that. Any integer n greater than 1 is divisible by a prime number. Let's hit some counterexamples. Here's my statement for all integers a and b. If a divides b and b divides a, then a equals b. This is going to be false. Again, it might take you a while to figure out an actual counterexample. This is why sometimes it helps to write a couple examples out. And sometimes it does even help to write the definitions out. Here I've got from the b divides a and the a divides b. I can make those two statements. And again, if we try to work through all of that, basically we'd have to conclude that h and k are divisors of 1. Well, if we remember our earlier theorem, the only divisors of 1 are 1 and negative 1. So the only options then for h and k are either both 1 or both negative 1. Well, if they both equal 1, then b equals a. But if they're both negative 1, then b equals negative b, and they are different. That does suggest a counterexample, and basically those are numbers where they're almost equal, but one's positive and one's negative. So you can hopefully see some of the algebra and thought process behind it, and we did finally get to our counterexample as well. Let's talk the unique factorization of integers, because that's a pretty big deal. You may have heard this in a previous math class, but every integer, we can write it as the series of prime numbers that are multiplied together. So here's how we could write 72. Now I can write them in any order I please, but no matter what order I write them in, I should have 2 3s and 2 2s, or 2 3s and 3 2s. Sorry, that's hard to say. And what we're saying is that's the only way we can write 72. Again, we're not worried about the order that we're writing those terms. That is called the unique factorization, or the fundamental theorem of arithmetic. It's a pretty big deal. That definition might look a little scary, but basically we have some prime to some positive integer power times a prime to a power times a prime to a power, and so on. And again, each of those primes are different. Doesn't matter if the exponents are the same or different. And again, the order in which we write them does not matter. Our standard one, usually we'll have the largest one first, and so on till the smallest, just because it's a little bit easier to write it that way. So let's say I've got 3,300, and I would like to write it in that standard factored form. So let's start by finding the factors of that. Let's start by writing it as 100 times 33. 100 is 4 times 25. 33 is 3 times 11. And of course 25 is 5 times 5. So I've got 2 squared, 3 to the first, 5 squared, and 11 to the first. And this would be my standard factorization. All right, let's try a slightly trickier problem. Suppose m is an integer such that all of that equals all of that. Does 17 divide m? So I can see 17 on the right. I do not see 17 on the left. And of course 17 is a prime number. So it's one of the primes on the right hand side. We've got a couple other primes in there, as well as some composites. That means it must also be a prime factor of the left-hand side, because we've said that these two things are equal to each other. And needless to say, all of these numbers on the left, well, they aren't 17. So because 17 isn't in any of them, and because these are equal, 17 must be either m itself or one of the prime factors of m. So we would say that that is a true statement. And that is everything in section 4.4.